Okay. So thank you very much, Josh, for this invitation. I'm very happy to be here with you at distance online to present this work, which is about infinite horizon difference games. Some of it has been already presented in Valladolid when Guiomar invited us this summer, and it was a very nice conference. We still think of it, and then I changed a little to be able first, because it was a 25 minutes conference, and now it's a little longer, and I added some other notions in this place so you can see. So what about the problems that I'm going to talk about? So no, come on. Yes, so the difference game I'm going to work on is a game with M players. In this game, so M players, for every J going from 1 to M, U underline U sub J will denote the strategy of player J, and U sub minus J, as usual, will denote the other player's strategies. So the problem is the following: for every player J equals 1 to M, we want to maximize the function J sub J of X, Uj, U minus J, which is the infinite series of the phi Jt at xt, Ujt, U minus Jt. I will explain all the details just later. And the dynamics are given by a difference equation xt plus 1 equals ft xt ut, or a difference inequality xt plus 1 less than or equal to ft xt ut for all t in n. An initial condition is given, x0 is equal to eta. Now, x is called the state, as you know, of the game. Eta is just un clin d'oeil to the state. So what is the aim, in fact, of this work? The aim is to provide necessary conditions, namely Pontryagin maximum principles for these dynamic games. So we are in discrete time, as you noticed. The aim is to provide conditions in finite dimension or infinite dimension. I will show you where does this enter, and in infinite horizon, since here you notice that we are in infinite horizon. Now, when I say provide necessary conditions, I will talk very quickly at the end about sufficient conditions also. But my aim is really to give necessary conditions. Now, the necessary conditions in the form of Pontryagin maximum principles will be of two kinds. There will be conditions called weak Pontryagin maximum principles and conditions called strong Pontryagin maximum principles. And this will appear because I will talk in each case of both of them. Very quickly, what is the difference? When we talk about weak principles, it means that we will say that the strategy, the optimal strategy, will be such that the differential of the Hamiltonian with respect to the strategy at that optimal strategy is 0. Whereas if we talk about strong Pontryagin maximum principles, we have that the strategy, the optimal strategy, gives the Hamiltonian the highest value among all the admissible admissible strategies. So let us start to explain a little what is in this game, the control dynamical system. So I am working in a subset xt, which is non-empty, open, of Rn. Uj sub t for every j is a non-empty subset of Rd. So I will call U sub t, the big set U sub t, the product of all these sets, subsets, and I define a function ft, which is from xt times ut into Rn. With these elements, we can define a difference equation, xt plus 1 equals ft xt ut, or a difference inequality, xt plus 1 less than or equal to ft xt ut. Now, in fact, if we were in the continuous time case, we would have here a differential equation. So in discrete time, I call it a difference equation. What are the underlying x? The underlying x is the infinite sequence of the xt's, which belongs to the infinite product of the xt's, the sets, the subsets xt's. The underlying u, which is composed of underline u1, underline u2, underline um, the sequences of strategies of each of the 1 to m players, is a sequence also ut, which is in the product of the infinite products of u1t, umt. Now, I want to talk about admissibility or feasibility. When do we say that process x, underline ug, so a process which is formed of state and strategy of uj, it will be feasible or admissible with respect to a given strategies of the other players if it belongs to the set pi xt product of the xt's time products of the ujt's, and if it satisfies the difference equation given the strategies of all the others and, of course, the initial condition. So I put a small e here to denote that it will be admissible when we have a difference equation, and I put an I to indicate that this is the problem with the difference inequality. So when do we say that a process formed by the state and all the strategies of the players is feasible or admissible? When it is in the correct set and it satisfies the difference equation and the initial condition. The same for for a process, let us say, of strategy and state and strategies of all the players satisfying di, the difference inequality and the initial condition. So what are the criteria that we are going to work with? For every t, for every j, we define functions phi sub jt from xt times ut into r. And we define, so the j sub j of the state, the strategy of player j and the other strategies, which is the infinite series, the infinite sum of the phi jt at xt ujt u minus jt. Now, for the case of a difference equation or a difference inequality, we will define the notion of domain. So why do we talk about this notion? Because when you look at this series, you can say that there is no reason that the series will converge. So it can be undefined. This is why I will define the domain relatively to strategies u minus g to be the set of all the admissible processes, state and strategy of of g, such that the infinite series converges given u minus g. And the domain, when I don't precise where I want to talk about all the strategies of the players, will be the set of all the state and strategies of all the players which are admissible and for which the infinite series converge. Okay? So since we don't have that the infinite series always converges, we have to define different notions of Nash equilibria. So first, I want to precise, because many of you will be asking me that question, I will be talking about open loop Nash equilibrium. Although it will not be subgame perfect Nash, I will talk about open loop Nash equilibria in all the talk. So a process in the domain of G will be called an open loop Nash equilibrium. I will not repeat open loop, but keep it in mind. A Nash equilibrium, if for all J going from 1 to M, the criterion at X hat uj hat, given u hat minus j, is greater than the criterion at any other admissible x uj, which are also in the domain, I mean, for which the infinite series will converge. Okay, so this is the usual definition. I put here, let A be in E or I, meaning that I'm considering the problems with a difference equation or a difference inequality. So following von Weizsäcker, who introduced this notion in the continuous time case, I will introduce the notion of overtaking Nash equilibrium. So for A in E or I, a process x hat u hat, an admissible process x hat u hat, will be called an overtaking Nash equilibrium. We will say one overtaking Nash equilibrium. If for all j going from 1 to m, the lim inf of the difference of the finite sums is greater or equal to 0. So the first finite sum is evaluated at x hat t u hat jt, which are part of the process x hat u hat, and I'm comparing it to other xt's ujt, which are part of the process, which is any other admissible process, given u hat minus j. So this is one notion. A second notion will be the weak overtaking Nash equilibrium, one. So a process given A in E or I, x hat u hat, an admissible process, will be called a weak overtaking Nash equilibrium if for all j going from 1 to m, the lim sup of the difference of the finite sums is greater or equal to 0. The first finite sum is evaluated at x hat t, u hat t, gt belonging to the admissible process in question, which will be called overtaking Nash, weak overtaking Nash, and compared to another, so here I forgot to remove the hat, x uj admissible. So with these three notions, we will proceed. Each player is going to solve an infinite horizon optimal control, which is parameterized by the strategies of the other players. So to talk about necessary conditions, this is what I will do. In the general case, you will see what I mean by general case in 2 minutes. In the general case, I will follow a method of reduction to the finite horizon that I will apply to each infinite horizon problem. The difficulty of subsequences of multipliers with non-zero limits. So I will add additional conditions to be able to extend my results of finite horizon to infinite horizon results. Now, when xt and ut are subsets of infinite dimensional spaces, we will get more difficulties. You will see why. I will show you how the weak star closure of the unit sphere will be the unit ball and hence will contain the origin. So my subsequences may go to 0. So this is why we need more conditions to avoid this case. Now the special case with respect to what I call the general case. The special case will be the case of the bounded processes. In this case, each infinite horizon optimal control problem will be studied as an abstract static optimal control problem in Banach spaces. And I will use results from functional analysis to obtain my results. So I put here this reference. It's the book written with Joël Blot in 2014. It's a book about optimal control in infinite horizon in the discrete time framework, but it contains many results that I will use here to generalize to the game case. So with this, I will set the Hamiltonian of the problem, Hj for every j going from 1 to m, Hjt of the state xt ut pjt plus 1 lambda j. These are the multipliers I will talk about. It would be the multiplier lambda j multiplied by the objective, by the criterion, by the objective function phi j. Plus, this is the multiplier, which is the adjoint variable multiplied by ft. And I will start by describing weak Pontryagin principles as necessary conditions. So given that we are working in a problem with the difference equation or difference inequality, let x hat u hat be a Nash equilibrium, an open loop Nash equilibrium, respectively an overtaking Nash equilibrium or a weak overtaking Nash equilibrium. If the following conditions are satisfied, that the phi jt for all j are all Lipschitzian on a neighborhood of x hat t, u hat t, and regular at that point. If ft is strictly differentiable at xt hat, ut hat, if ut is closed and Clark regular at u hat t, and if this is what I put in blue, this is a special condition that I will need for the infinite horizon. The partial differential d1 ft xt ut is invertible. Then for every j, there exists lambda j in R, a sequence pjt in Rn, n to the n, it's an infinite sequence. For every j, every t, pjt is in Rn. Satisfying the lambda g's are all positive, greater or equal to 0. The couple lambda j, pj1, when t is equal to 1, is non-zero. For all t, except t equals 0, pjt is in the Clark differential of the Hamiltonian, and for all t, it is the partial Clark differential with respect to the state, and this is the Clark partial differential with respect to uj, to the strategy uj. So this condition reduces when you had jt's in the interior of the set ujt to the condition that 0 belongs to the partial Clark differential with respect to the variable u2 uj. So if we are in the case of a difference inequality, we can add two other results to these four first one, which are that the adjoint variables will be positive, non-negative, and that we have the condition that pjt plus 1 times ft xt minus x hat equals 0. So we have the exclusion relation. Now, a second theorem, which is in the same spirit for A, which may be a difference equation for the problem with a difference equation or a difference inequality. Let hat x, hat u, the process be a Nash equilibrium, respectively an an overtaking Nash equilibrium or a weak overtaking Nash equilibrium. such that for all t, ut is in the interior of ut. And if we have the following conditions, these are easier to read. You see all the phi jt for all the players are Fréchet differentiable at xt ut. Ft is C1 of class C1. You know, class C1, it means that it's continuously Fréchet differentiable at x hat u hat t. And I add this invertibility assumptions, d1 ft hat xt hat ut. I will show you a little later how does it enter in this thing. Then the conclusion is that there exists lambda j in R multiplier for every j, pjt sequences such that, which are the adjoint variables, such that the lambda j is non-negative for each j. The couple lambda j pj1 is non-zero. We have the adjoint equation, which is pjt equals the partial differential of the Hamiltonian with respect to the state. And the second, the last condition is what I call the weak maximum principle of Pontryagin. In fact, the partial differential with respect to the strategy of the jth player of H of the Hamiltonian is equal to 0, okay? So, in fact, if I am looking at the case with difference inequalities, I can add, as before, the fact that the adjoint variables are non-negative and that we have the exclusion relations. And moreover, if I have that for every j, the partial differential of the functions ft with respect to ug is onto, then for every j, we guarantee that the multiplier lambda j is different from 0. So if you notice the following thing, when we have a differentiable function at the point z, then it is not necessarily locally Lipschitzian around z. We have examples of functions which are differentiable without being locally Lipschitzian at a point. And also, a locally Lipschitzian function around z is not necessarily differentiable at z. So I'm saying this to tell you that none of the two previous theorems, none of them is a corollary of the other. So each one is really independent of the second one, okay? Now we can see that the notions of locally Lipschitzian, we can try to think of them as to generalize the continuous Fréchet differentiability. So these are two separate results. To show a little how these hypotheses enter in this, I decided to give a quick sketch of the proof of the second theorem, since this one implicates only the differentiability, the Fréchet differentiability, and the class C1 of the function. So it will be a little easier to look at. So let t be a fixed number. I will start by looking at a reduced problem. So why I am doing this? I'm doing this because I want to tell you that I started saying that I will look at the problems in the general case by starting with a method of reduction to the finite horizon. So now I'm writing a problem in finite horizon, which I call the reduced problem. So given any integer t, which is non-zero, I will define the process bold xt, bold u capital T, to be the process of the two truncated sequences. I am stopping them at T, capital T. And I am defining this criterion, the J sub J, which is indexed, upper indexed by capital T. It's a function of bold xt, bold ut. It is the truncated sum. T goes from 0 to big T. So the following reduced problem will be for all J going from 1 to M, every player, which is player 1 till player M, will maximize J sub J T of xt ut, which is submitted to the difference equality, the difference xt, the difference equation, xt plus 1 equal ft xt ut, but for t going from 0 to t, not all t's, of course, x0 being equal to eta, and x at t plus 1, capital T plus 1, being equal to hat x capital T plus 1. We will see what is this. I call it the problem P, upper indexed by capital T. So why am I doing this? Now, I did not write it, but you can think of that also. You can think that I have a second problem, which is the same, but instead of having the difference equation, I have a difference inequality. So it will be also in the same spirit. So I have a proposition that will allow me to continue by using the reduced problem. So if I start with a process, hat x, hat u, which is a Nash equilibrium for the problem, for the first problem, respectively an overtaking Nash equilibrium, a weak overtaking Nash equilibrium, and I choose a t, which is non-zero and non-zero integer, then the restriction of that process to big T, so if I take the truncated sequences, x, bold x hat T, bold hat ut, this process will be a Nash equilibrium of the finite horizon problem that I wrote here. Okay? So starting with a Nash equilibrium or an overtaking Nash equilibrium or a weak overtaking Nash equilibrium, I can say that the restriction of this process, when I stop at T, I stop at T by putting also that the value of xt plus 1 should be exactly hat xt plus 1. So now what I will do is taking the finite horizon problem and applying to the finite horizon problem known theorem, because in the finite horizon case, if I take every one of these problems for every j, I have an optimal control problem in finite horizon, and we have well-known results. So we can apply these results and say that if I have a t which is fixed, an integer big T which is fixed, and for every j going from 1 to m, there will exist lambda j indexed by t, a real number, a sequence pjt indexed by big T for every g, of course. Not all zero, this is very important. I cannot have that lambda jt and the sequence pjt are simultaneously equal to 0, such that we have the adjoint equation. It is the adjoint equation in finite horizon. And we have the maximum principle in the weak form. This, I wrote it this way I could have put the Hamiltonian the partial differential of the Hamiltonian with respect to the strategy of J is equal to 0. This is exactly what is written here. And this is written without the Hamiltonian. It means, in fact, that the PJT is equal to the partial differential of the Hamiltonian with respect to the state. This is what we have. But now you notice that I have this for every t. For every t, I can write such a thing. So for every t, I will have a lambda jt, and I will have a sequence pj, which is indexed by big T. But the aim is now to get rid of the big T and to get a lambda j in R and a sequence pj, which will be not as this sequence. You notice that this sequence that I obtained in the finite horizon problem, it is a sequence, a truncated sequence, because t, small t, goes from 1 to big T plus 1, okay? What I want is a real number in R and a sequence P sub JT, which is where T is in big N, okay? I want an infinite series, so I don't want the dependence upon T. So how can I extract from these sequences or subsequences which will do the work? So this is what I will look at, extracting subsequences. So now enters the invertibility hypothesis, because this one will allow me to transform the backward. You see that this equation, the adjoint equation, is a backward equation. So if I put the hypothesis that for every t, d1 ft x hat t u hat t is invertible, I will be able to transform this backward equation into a forward one. So I wrote it this way: pjt plus 1 is equal to pjt circle mt plus lambda jt times njt. So I did not develop what is mt and jt. You can see from here what are m and n, but it's easier to read it this way. So since I have done this, I will get the following result. Assume that lambda jt and pj1t are both 0. So assume that the multiplier, the lambda j multiplier, is 0, and pj, when small t is equal to 1, is equal to 0. This, if you notice very quickly here, will imply that pj2 is equal to 0. And then, of course, I will iterate to get that all the pj sub t to the big T are 0. But this contradicts my given here, the result that I obtained in applying the finite horizon theorem, that the lambda jt and the pjt must be not all 0. So since I have this contradiction, taking the contrapositive will guarantee that the couple lambda j to the t, pj1 to the t is non-zero. So this is very important. The non-triviality of this couple will be very important for the rest. Since it's non-zero, I am able to normalize it. Okay, so absolute value of lambda jt plus the norm of pj1t equals to 1. When you have this, notice that we have this for every big T, for every big T in N, in the set of integers. So it's very easy to see that for every T, the sequence lambda j big T, that the sequence lambda j t is bounded, okay? because for every big T, we have this equality. So for every T, lambda JT is less than 1. So the sequence, which is indexed by big T, is bounded. And the same for the sequence Pj1, which is indexed by big T. This sequence Pj1 indexed by big T is also bounded. Now, having this result, after some work, we can show that the PJTs, because of this, are also all bounded, okay? Because here I only have that PJ1 is bounded, so I have then that for every small t, we can have that these are bounded. For every small t, the sequence indexed by big T will be also bounded. So now I use a Cantor's diagonal argument because it needs to have compact subsets to work in it. This is what we obtained. So I can get limits of my subsequences such that lambda j plus pj1, which will be the limit of the subsequences, will be equal to 1. And for every small t, I will have the limits of my subsequences for every t will satisfy these two conditions, but now it is not for pt, it is for any, it's for pjt and lambda j. Okay, so I get this, and it will be true for every t. So using this Cantor diagonal process, this is the key to obtain subsequences that will converge. And since I have this condition, okay, I'm sure that they do not converge to 0, okay? So now, after having looked at the invertibility condition, I will write theorems with other conditions. So without giving you some proofs, I will just show you that in case we use only the difference inequality, and we get the problem with a difference inequality, given that x hat u hat is a Nash equilibrium, respectively, an overtaking Nash equilibrium or a weak overtaking Nash equilibrium, such that u hat t is in the interior of ut, and given that we have good smoothness conditions on phi jt, which are Fréchet differentiable, and ft must be C1, if instead of the invertibility condition, I write these positivity conditions, okay, the partial derivatives of the functions ft, k with respect to xs are greater or equal to 0, but with respect to xk, they are strictly positive, then I can get the conclusions of the previous theorem with inequalities, with a problem with inequalities. So the proofs look a little the same, but of course I cannot use anymore the invertibility. I have to use these conditions to be able to have subsequences not converging to 0. So when f is a production function, the condition 2, this condition is coherent with what we know from, with the economic theory. And this condition implies that the partial differential d1 ft is a non-negative matrix, of course. Now, notice that this positivity condition does not imply the invertibility of d1 ft ut when n is greater than 1. Of course, if n is equal to 1, the two conditions are the same. But if n is greater than 1, if we take an example, if, for example, all the partial derivatives are equal to 1, okay, for all I and j, then you have a square matrix which contains 1 at every place. Thus, the positivity condition is fulfilled. But this matrix is not invertible. If you have a matrix containing, take a 2 by 2 matrix, which has 4 ones, the determinant is equal to 0, so it is not invertible. Okay, so the positivity condition does not imply the invertibility and vice versa. Now, I talked about this theorem that I could obtain if I have difference inequalities. Indeed, the proof uses the difference inequalities. But we have the following good results. If phi jt is increasing with respect to xt, if the objective functions for every j are increasing in the state variable and ft increasing in the state variable, then we have the following good result, which is easy to show. If the process is an overtaking Nash equilibrium for the problem with a difference equation, then it is also an overtaking Nash equilibrium for the problem with a difference inequality. Therefore, having this result, you can see that I can write the previous theorem with a difference equation, at least for the problems when x hat u hat is an overtaking Nash equilibrium. Of course, also for the problem where it is a Nash equilibrium, because if it's a Nash equilibrium, then it's an overtaking Nash equilibrium, and then you can say that it's an overtaking Nash equilibrium for the problem with difference in equation. I don't know how to do it for weak overtaking Nash equilibrium, but for Nash equilibrium and overtaking Nash equilibrium, these conditions will work if you are in a problem with difference equations instead of difference inequalities. So far I have only discussed weak Pontryagin principles. So we have also necessary conditions for giving strong Pontryagin principles. Now what we have is conditions that will look a little different from what we had before in the following sense, starting with a Nash equilibrium or an overtaking Nash equilibrium or a weak overtaking Nash equilibrium. We have that here the functions phi jt and ft should be of class C1 only with respect to the state, because I will not derive with respect to the control, with respect to the strategies. I also have the conditions of invertibility on D1 ft. I need the set of states to be convex, and I need a convexity condition. I will talk about it a little later. And notice that when we are working in continuous time problems, we don't need convexity conditions to obtain results as strong Pontryagin principles. This is particular to the discrete time case. So in this case, there exist multipliers lambda j, p, jt, sequences, adjoint variables, satisfying the lambda j non-negative, the couple lambda j page j1 non-zero, the adjoint equation. And here, instead of the weak Pontryagin principle, I have the strong Pontryagin principle, which is in the form of a maximization of the Hamiltonian with respect to the strategy U sub j, the strategy of the jth player, and you can see that it should be done along the optimal state. Okay, so it's a maximization of the Hamiltonian. Of course, if we are working with inequalities, we add to this the two conditions on the sign of the variables, of the adjoint variables, and the exclusion conditions. So the convexity condition, you see, it's quite a complicated convexity condition. It's due to Yoffe-Tikhomirov in the control problems. It means that if you have for every couples of U prime J, U double prime JT, you should be able to find there exists a U hat JT such that you have this condition, which looks like what we have. It's like a convexity, a concavity condition. Okay, you will have the equality for the FT in case we work in a problem with difference equality, and inequalities. For the inequalities, we will need a kind of concavity. So this condition, which complicated condition, is complicated to write, not to think of. It is implied by usual convexity condition that you know very well. It is implied by, for example, all the phi jt's being concave with respect to the strategy of the jth player, the ft affine in uj, and when A is an equality, we have the ft should be affine, and if we have inequalities, the ft should be concave with respect to the u sub j. Okay, so we don't need such condition in the continuous time case. You have also a similar theorem if instead of the invertibility condition, I put positivity conditions, you can get the same results. So let me go quickly to the bounded case. The bounded case, which is a little now different to work with. I will take only the equality, the difference equations. I will not look at difference inequalities because it will necessitate more hypothesis, but it can be done, of course. Now I will put that phi jt is beta to the t psi jt, and for simplifying the everything, I will put that ft is equal to f. So if x hat u hat is in L infinity times L infinity, so I want my x hat u hat to be bounded. So if it's a Nash equilibrium, and here you will see that in this problem, the overtaking Nash equilibrium, weak overtaking Nash, and Nash will be all the same because of the boundedness. So assume that we have good conditions, the psi j and the f are of class C1. We have these conditions on the soup of the norms of the partial differential of f with respect to the state. Then there exist adjoint variables. What's good here is that my adjoint variables, I'm going to find them in L1, such that I have the adjoint equation. This is the weak Pontryagin principle because I'm in the weak section. And I have condition C, which is a transversality condition at infinity, which says that limit of pjt is equal to 0 when t goes to infinity. This is a very interesting thing because in general, we don't have it. In other discrete infinite horizon problems, we don't have necessarily this condition, as you have Halkin, which showed this in the continuous time case. But in the case of bounded processes, we have that this condition is obtained since it is obtained since pjt is in L1, okay? So we necessarily have that limit pjt is equal to 0. So this is interesting. It's given. Now another theorem of the same spirit, but with some more conditions, convexity conditions, will give me results for strong Pontryagin principles. So the same spirit, we have also the adjoint variables in L1, in the space L1. So a sketch of the proof very quickly would be to write the problem as an abstract static optimization problem in a Banach space of the form maximize j sub j of xu, f xu equals 0, and x uj is in L infinity times u. We show that our problem satisfies all the hypotheses of known abstract theorems in Banach spaces for the weak and the strong case. We apply the abstract theorems, but when we apply them, we obtain the existence of non-zero multipliers. The lambda j will be in R, but the other will be in the dual of L infinity. But now the dual of L infinity, it is not L1, is not L1. The dual of L infinity is L1 plus something here, L1D, and I want to get rid of this L1D. This is what will be done. And this L1D, what is this L1D? If you look at it in L1D and R, it's all the singular functionals. In fact, if you have a theta, a linear functional, which is in L1D, it means that there exists a K in R such that for all the sequences which are in the space of convergence sequences having a limit in R, theta applied to the sequence is K times the limit of the sequence. Okay, so now just one word and I will stop if you want to ask me some questions. I said that I had to also introduce the infinite dimensional case. So in all my previous theorems, you notice that X was Rn and U was Rd. Now, I can imagine that X and U are Banach spaces. So I have the same configurations. Xt is a subset, open, non-empty subset of a Banach space, not of Rn, Ujt of a Banach space U, and I have the same thing. I have a difference equation as in the problem. So the theorem is the following one. We have many theorems. I choose to put only this one. If X hat, U hat is a Nash equilibrium, respectively an overtaking Nash, a weak overtaking Nash, and assume that we have the following conditions, that Xt is a non-empty open convex subset of X, Ut non-empty convex of U, X separable, the phi Jt Fréchet FTC1, till there nothing is so different. The partial differential invertible, we already had this condition. I add the new condition, image of the second partial differential with respect to Uj of Ft is closed and of finite dimension or else of finite codimension. Then for all T, this I'm writing a result for every big T. It's a finite horizon result if you want. Okay, so there exist multipliers and there exists a truncated sequence of adjoint variables, which is here, no more in Rn, but in the dual of X, in the dual of my Banach space. So the conditions, they are non-zero, these two, the same, exactly, an adjoint equation. This is the weak principle, okay? It's written with an inequality because I'm looking at it at every Uj minus U hat Jt. And now I can write the infinite horizon theorem. If I have a Nash equilibrium, an overtaking Nash, a weak overtaking Nash, and with the previous assumptions, if I add to it that for all J, the tangent cone of Uj1 at the point Uj1 is a vector space, and if I have this a little complicated technical condition, then I can conclude that there exists, I can assure that the lambda J for every J will be non-zero and that there exists an infinite sequence in the dual of X, of the Banach space, satisfying the conditions that are here, the adjoint equation, Hamiltonian, the weak Pontryagin principle. Okay, so a sketch of it will be, I will not show you the sketch, but the thing is that when I normalize as I had normalized before, what I have here is that I cannot use as before the compacity, that the compactness that I got, but I can talk about the Banach-Alaoglu-Bourbaki theorem in a separable Banach space to obtain sequential compactness and weak convergence star. weak star conversions to a limit, and then technical work will allow me to get my results. So I will not talk about sufficient condition. I will just tell you, thank you very much for having accepted to follow.